Hi, in this video I'm going to continue with section 7.6 that we started last time. But let me quickly recap what we did last time. If you recall from the last lecture, we looked at why we need to study the step function. It helps us with solving differential equations that involve discontinuous forcing functions. It makes solving those types of problems really easy. So we looked at motivation. Then we looked at how to take a piecewise, then we looked at what a step function is, unit step function. Okay. Then we took a look at how to take a piecewise function and write it as a step function, unit step function. And then we also did where we took a unit step function and we wrote it as a piecewise function. And lastly we did is we found the Laplace transform of the unit step function. So these are the things we did last time. And we want to build on that. So now that we know how to take Laplace transform of a unit step function, we also need to look at what happens when you're working with inverse Laplace transforms and how do step functions get involved with that. So that's what we're going to start with today. So today we're going to, so this is last time, today we're going to work on the inverse of something that ends up giving us a unit step. Okay. Then we're going to take a look at solving initial value problems with discontinuous forcing functions. Okay. And lastly, we'll take a look at periodic functions and Laplace transforms. And if we have time, I will also talk about the gamma function, which is a really important function in science. Okay, so these are the four things that are left. So it depends upon time whether we do the last thing or no, but that's what's left. So let's continue. So before I show you how to take Laplace transform of something that results in a step function, let's quickly review property 2 that we did last time. Okay, so this is property 2 that I gave you last time. It said that the Laplace transform of some function f of t plus a times u of t plus a, oops, it is t minus a, sorry, okay, is equal to e to the minus as times the Laplace transform of little f of t, which we can write as big F of s. Okay, all right. If I were to take inverse Laplace on both sides, now this property by itself is not very useful because very seldom are we going to take Laplace transform of a function which is shifted at the same point as a step function. Very seldom that's going to happen. Okay, most of the time we'll end up with something like this and we can't use this property. All right, but the inverse of this property is extremely useful. So if I take inverse Laplaces on both sides, I end up with this really useful property which tells us that e to the minus as of big F of s is equal to f of t minus a and u of t minus a. So that's what we end up with. This is an extremely useful inverse Laplace transform formula. Extremely useful. Okay. Now, let's take a quick look at this, how this works. Okay. This is also referred to as the second shift theorem. I gave it to you last time. So anytime you're taking inverse Laplace, that involves an exponential, then that exponential is going to result in a step function that's shifted by a units. So anytime you have an exponential whose inverse you're doing, that's going to result in a step function here. And then what will happen is you're going to take this guy, you're going to take inverse Laplace of big F of s, which will result in little f of t, and then you're going to shift that here by a units also. So when we're doing inverse Laplace of functions like this, where we have big F of s multiplied by some exponential, then that exponential will result in a step function. And then you take the inverse of big F of s, and whatever function you get, you shift that to by a units. Okay, so let's take a look at two examples really quick. So let's say that I ask you to find the inverse Laplace of e to the minus pi s times, okay, 3 over s squared plus s over s squared plus 1. I want to find the inverse of this. Okay. All right, so let's take a look at it. What's the first thing you notice? I'm taking inverse Laplace and I have an exponential of some, and then you're going to take inverse Laplace of something. So I'm going to get something here. This is going to result in that. And this exponential is going to result in a step function, u of t minus pi. That's what that exponential is going to result in. So we already know that. Now what do we do? Just like out here, if you notice, the exponential resulted in the step function. A is pi here. Okay. Now we take the inverse of each of these. So let's do inverse of 3 over s squared. 3 is a constant, so you get inverse of 1 over s squared. So you just get 3t. Okay. Now what are we going to do? We're going to take this function, little f here, and we're going to shift it by a units. A is pi. So we get 3 times t minus pi. So we're going to shift that. Then we have a plus sign. Then we take the inverse of this guy. If you take inverse of that you should recognize, it is just cosine of t. And we're going to take that, which is this guy now, and we're going to shift that too by a units. A is pi, so we'll get cosine of t minus pi. Okay, that's what that results in. So let's take a look at it. What is cosine of t minus pi? If you were to use the double angle identity for cosine, you'll notice that this results in just negative cosine of t. So you get cosine of t, cosine of pi, plus sine of t, sine of pi using the double angle. Sine of pi is 0. Cosine of pi is minus 1. So you get negative cosine of t, which is what we have. So I can rewrite this as 3t minus 3 pi minus cosine of t u of t minus pi. Now out here they just asked us to find the inverse, so we did that. One of the things you should get into a habit of is, if you're solving, again I want to stress this, if you're solving a differential equation and you end up with this, don't ever leave your answer like that. Write it without the step function. That means you want to write it as a piecewise function. So let's do that. Okay. Now, when does this function come on? It comes on at pi. So if you think about it, it comes on at pi. Until pi, this function is going to be 0 because you can only take on two values, 0 and 1. Before pi, the value is 0. And remember, t always represents time, so we're going to start at 0. So 0 is less than t is less than pi, less than or equal to, and t is greater than pi. That's my cutoff. I have two regions here. And we start at 0 always. Okay. So now, if you go from 0 to pi, since this u function is off, its value is going to be 0. So if you take 0 multiplied by all of this, you're just going to get 0. And after pi, the value of this function is 1. So if you take 1 times this, we just get that. So that is what the answer should be written as if you're solving a differential equation. We weren't solving a differential equation, so we could have left it this way. But eventually we want to solve differential equations that result in step functions. So we want to write our answers as a piecewise function, always. Okay. All right, let's do one more example of this, then we'll take a look at how to solve problems using step functions. All right. So we want to find the inverse Laplace of e to the minus 2s over s squared plus pi squared plus e to the minus 3s over s plus 2 squared. Okay, we want to find the inverse of this. We don't know what that is. Now, we notice that we have an exponential here, right here. So that will result in a step function, u of t minus 2, plus, this plus comes from here. I have another exponential that will also result in a step function, u of t minus 3. By the way, both of these I could have written this as what? Another short form of this is what? U of 2, and I could have written this as u of 3, just so you know. Okay. Now I just need to fill these brackets. So let's start with what's left if you ignore that exponential. So what do we have? I don't have room on the right, so I'm going to do it bottom. So I want to find the inverse Laplace of 1 over s squared plus pi squared. This is another one you should recognize. This looks a lot like sine, provided I had a pi on the top. So what I'm going to do here is I'm going to multiply by pi on the top, and I'm going to divide by pi to negate that. Okay, so that will result in 1 over pi times sine of pi t. Okay, that's what it's going to result in. Now what do we do? Because of this e function, not only do we get a step function here, but we also have to shift this function. So we get 1 over pi times sine of pi times t minus 2. So we shift that by 2 units. Okay, that's what we end up with. Now what do we do? Well, let's take a look at the other one. So I'm going to erase this side row. We want to find the inverse. If you ignore the exponential for a second, we have this 1 over s plus 2 squared. So what does that look like? Well, let's take a look at it. If I didn't have this 2, it'll just be s squared. So the inverse of that would be just t. But because of the 2, it's going to be an exponential, so it's going to be e to the negative 2t. Okay, so let me write that down. E to the negative 2t times t, because that's what that plus 2 does. It shifts the Laplace of this guy. Okay, that's called the first shift theorem, if you recall. Okay, all right, so now that we have that, that will go here, except because of this exponential, I need to shift this by 3 units, all the t's. So we get e to the negative 2 times t minus 3 times t minus 3. So that's what we end up with. Okay, all right, so let's quickly also learn to write this as a piecewise function. So this would be the answer, since we just want to find the inverse. We are not solving a differential equation here. So this would be a perfectly good answer. But let me show you how to write this as a piecewise function. So if you look at your times, I have t is 2, I have 3. So I have, and everything starts at 0. So I have one time zone, one piece, second piece, and third piece, so 3 regions. Okay, so I have 0 is less than t is less than 2. I have 2 is less than t is less than 3, and t is greater than 3. Again, the equalities, it doesn't matter where you put them till you put them in one of these pieces. Okay, now let's start with this. This one comes on at 2. So until 2, it's going to be 0. Okay, until 2. So this is 0 until t is equal to 2. So this function is 0. I'll use a green color for that function. This function comes on at 3. So until 3, this is 0. So I'll use this blue for that. Okay, so between 0 and 2, both of these functions are 0. So if you take something multiplied by 0, something multiplied by 0, we're just going to get 0. Now between 2 and 3, what's going to happen? This green function is going to be 1 after 2. Do you agree? After 2, this green function, this function will come on at 2 and it'll stay on. So it'll be 1 after that. And this other step function here, u, comes on at 3, and after that it's going to be 1. So it's going to be 1 after that. So let's see what happens between 2 and 3. Between 2 and 3, this is 1 now. This green function is 1. And this blue function is going to be 0. So this is gone. So you're left with 1 over pi sine of t minus 2 pi. I'm just writing the pi at the end. Okay. Now what happens? After 3, both these functions are on. So this is 1 and so is this. So you get this plus this. So we get 1 over pi sine of t minus 2 pi plus e to the minus 2t minus 3 times t minus 3. That's all coming from here. So this is the final answer. Okay. All right. So now let's take a look at some examples on how to solve differential equations that involve discontinuous forcing function. Okay, so we're going to take a look at that next, right? So keep that in mind. The whole reason for studying this section was to be able to handle discontinuous forcing function. So let's do that. So I'm going to call this D. Okay, so solving discontinuous forcing functions. using Laplace transforms. So I'm just going to do an example. That's the best way to do this. This is fairly straightforward. There's no magic to this or anything like that. Okay, so keep that in mind. I'm going to try to do 2 examples and go from there. So we have y double prime plus 3y prime plus 2y is equal to g of t, where g of t is my forcing function. They've given us some initial condition. Y of 0 is equal to 0 and y prime of 0 is equal to 1. Now this is the example I started this section with, the motivation of this section, if you go back and look at it. Okay, so we're going to do this same problem using Laplace transforms, where g of t is equal to 1 if t is between 0 and 1, and 0 if t is greater than 1. That's how we define that. All right. Now the first thing we're going to do is, before we do that, we're going to rewrite this this ODE that we're starting with using step functions. Now this is discontinuous, so how we write, we get 1 times u of 0 minus u of 1. This is what you guys did for homework when we wanted to write this piecewise function. So we took a piecewise function and wrote it as a unit step function. You guys follow? That's what we did. All right, so we did that. The rest is exactly what you did in section 7.5. So there's nothing more I can teach you after that. You already know the rest. We start by taking Laplaces on both sides. So Laplace of y double prime is s squared times big Y minus s times y of 0 minus y prime of 0 plus the Laplace of 3 times y prime. So it'll be 3s times big Y, okay, minus y of 0 plus 2 times Laplace of little y, which is big Y, is equal to Laplace of this guy. This is just 1, so if you distribute, you're just going to get u naught minus u1. Laplace of u naught, so if you recall, Laplace of u of t minus a, or u of a, whatever you want to call it, is e to the minus as over s. That's what it is. In our case here, a is 0, so you get e to the 0 over s, so you get 1 over s, minus Laplace of 1, so you get e to the minus s over s. Okay, now we can go ahead and introduce our initial conditions. Y of 0 is 0 and y prime is 1. So this is 0, this is 1, this is 0. And then everywhere else I'm left with some big Y's. I'm going to collect those. So I'll pull the big Y out. So I'm left with s squared plus 3s plus 2 is equal to 1 over s, okay, minus e to the minus s over s. And then I'll move whatever is left to the right hand side on this side. Remember, don't forget this. This is left here because this is 1. So you have negative 1 here. When I move it, it's going to become a positive 1. Okay. The next thing we're going to do is, I'm not going to combine this e term with anything else because that's an exponential, but these two terms I can combine. So I have 1 over s plus 1. So that'll just be 1 plus s over s. That's what that is. Okay, so let's go ahead and divide by this then on both sides. So you get big Y is equal to 1 plus s over s times s squared plus 3s plus 2 minus e to the minus s over s times s squared plus 3s plus 2. So that's what we end up with. Now at this stage we have a couple options here. Okay. Now I do want to stress something very, very important. When we do partial fraction decomposition, you should have a polynomial on the top and polynomial on the bottom to do that. I cannot do decomposition with this because I do not have a polynomial on the top. So if you want to do the decomposition with that, you need to rewrite that. So let me show you. So we get 1 plus s over s times s plus 2 times s plus 1 minus, you take that e to the negative s out, and now we can make it into a rational function like this, s plus 2 times s plus 1. So keep that in mind. You can only do decomposition if the numerator is a polynomial. So if it's not a polynomial, take that expression out and do the decomposition for this. Okay. Now I can actually cancel this. I'm not going to go through the partial fraction decomposition. You guys know how to do that. So let's pretend that I did PFD. You guys do need to do those things by hand. So you get big Y is equal to 1/2 over S minus 1/2 over S plus 2 minus e to the negative S times, you do the decomposition for this, we get 1/2 over S minus 1 over S plus 1 plus 1/2 over S plus 2. So that's what we end up with. Okay. Now the next thing I want to do is do the inverse Laplace. So in the inverse Laplace of big Y is little y of t. The inverse Laplace, half is a constant, so you get 1/2 over 1 over S. Inverse Laplace of 1 over S is what? T over 2. 1/2 t, or actually, no, I'm sorry. If it was a square, it would be t over 2. It'll just be 1/2. Because the inverse Laplace of 1 is 1 over S. So the inverse of this would be just 1. Okay. This one will give you minus 1/2. When you take inverse of 1 over S plus 2, that'll give you e to the negative 2t exponential minus, what does this introduce when we do inverse Laplace? What did I talk to you about earlier? Anytime you see an e and you're doing inverse Laplace, that introduces a step function. So you get u of what? Where's the step occurring? At 1. So u of 1. Okay. Times, now you take inverse Laplace of each of these and remember to shift them. Okay. So we get 1/2, inverse Laplace of that is just 1/2, minus inverse Laplace of this is e to the negative t, but then you're going to shift it by whatever a is. Out here a was 1, that's this value. So you get e to the negative t plus 1. Oops, it should be t minus 1. Okay, so that's what you'll end up with. Plus, same thing over here, I have 1/2, that's a constant that pulls out. This gives you e to the minus 2t, and you'll shift that too. E to the minus 2 times t minus 1. I want to keep writing plus for some reason. And there's your answer. Now, since we were solving a differential equation, you should never leave this like this. We should write it as a piecewise function. Okay, so let's do that. All right. I only have one step function. So if you think about your timeline here, this is 1. We always start at 0. So I have how many regions here? 1, 2. And this function comes on at 1. So it becomes 1 after 1. And prior to that, it's always going to be 0. Right? So if it's 0 before that, so from 0 to 1, t, if you're in the interval 0 to 1, this function is going to be 0. If it's 0, this whole right-hand side is gone. So all you're left with is this. So you get y of t. We get 1/2 minus 1/2 e to the negative 2t if 0 is less than t is less than 1. Then what happens to the right of 1 when t is greater than 1? This u function is going to be 1 now. So you're going to multiply all of this by negative 1. So we get 1/2 minus 1/2 e to the negative 2t minus 1/2 plus e to the negative t minus 1 minus 1/2 e to the negative 2t plus 1. I keep writing plus today. T minus 1. These halves will cancel, and there's your answer. The cool thing about this is if you were to graph this function, you can use Mathematica, MATLAB, or whatever graphing tool you want to use. If you were to graph this function, you would notice that this function, the forcing function, was discontinuous. You can see that. If you were to graph that, you would see this is t, this is g, this is 1, 0, and this is 1. Between 0 and 1, this function is 1, and after that it is 0. So there's a discontinuity out here in the forcing function. But look at the solution. If you were to graph this solution, it starts at 0, it's going to peak, and then it's going to die. why is it going to die? Because these exponentials, as t goes to infinite, you get this will be infinite. You get e to the minus infinite, that'll be 0. This will go to infinite. Negative 2 times infinite is negative infinite. E to the minus infinite is 0. This is 0. So everything will go to 0. As t goes to infinite. Infinite means it's bigger than 1. So here is where this peak occurs at 1.13, but the discontinuity was at 1, and you can see this function is not discontinuous at 1. It is nice and smooth. We always want our solutions to differential equation to be smooth, and we want them to be continuous, so we can predict what's going to happen in the future. All right, so I skipped a lot of parts over here. Well, not a lot. I just skipped one part, doing partial fraction decomposition. You still absolutely need to do those by hand. I just didn't do them for the sake of time. Let me do one more example of this. Okay, let's do something a little bit more complicated that involves a lot of moving parts. Okay, so let's take a look at that. So let's say if you have y double prime plus 4y, okay, is equal to g of t, and they've told us that y of 0 is equal to 0 and y prime of 0 is also 0. So the initial conditions both are 0, so that's nice. Where g of t is a little bit more complicated. It is 0, okay, if t is between 0 and 5. It is t minus 5 over 5. Okay, if t is between 5 and 10, okay, and it is 1 if t is greater than or equal to 10. Okay, if you were to graph this, technically this is not discontinuous. If you notice, if you were to graph this, let's just quickly graph it. We have 5, 10, 0. So between 0 and 5, this function is always 0. So here it's always 0. There's a hole here. Okay. Then it's a linear function. This is a line then. Okay, with a slope 1/5, you know, and the y-intercept of -1. So that's what that line looks like. So it looks something like this. Let me do that. So let's say this is 5. Okay, actually 1, not 5. Sorry. There's 5 here, and then this is 1. Why is that in 1? When t is equal to 10, the value is 1, so I know it's going to end here. So I know that this function, when t is 5, what do we get? You get 5 minus 5 is 0, so you start right there. So you're going to go to 10, and then after that it's just going to be 1. So you can see this function is continuous, but it's made up of a lot of different pieces. So even if you were doing method from chapter 4, we'll have to do this problem 3 different times. And you can see that is a lot of work. Okay, we'll have to do the same problem 3 different times. First we'll assume it's 0, next time we'll put in this, next time we'll put in that, and we'll solve it 3 different times, and that's a lot of work. So instead of doing that, we can use Laplace transforms and step functions to make our life easy. So the first thing I'm going to do is rewrite this differential equation y double prime plus 4y using a step function. So let's do that. So the first part is 0, so it doesn't matter. I don't need that. This one comes on between u of 5 and u of 10. So let's do that. U of 5 minus u of 10. So that's going to be t minus 5 over 5 plus this one comes on at 10, so it'll just be 1 u of 10. Okay, so that's what we end up with. I'm just going to clean this up a little bit, combine some of those u functions that are the same. So we get t minus 5 over 5 times u of 5 plus I get 1 minus, okay, t minus 5 over 5 u of 10. So I distributed here and collected the u of 10s. That's all I've done. Okay. Now this is my differential equation. The nice thing about the step function is what it takes a piecewise function that has 3 different definitions and writes as a single function. So that's nice. All right. Now we can take Laplace transforms on both sides. So we get s squared big Y minus s times y of 0 minus y prime of 0 plus 4 times big Y, that's from there, is equal to, so now comes the fun part, to take Laplace of these guys. So what is Laplace of this function? Okay, if you recall, we're going to use this property here, Laplace of f of t times u of a, whatever u of a is. Okay, if you recall, we did this was property 3 that I gave you, if you recall that. So you can look through your notes and look for property 3, and you should have that. Okay, so what does that property 3 tell us? What is it? Laplace of f of t times u of a is going to be what? E to the minus as times the Laplace of f shifted. F of, now be careful out here, when most of the times when we are doing shifts, we're going t minus a. This time it's going to be t plus a. Okay, so let's see if we can do this correctly. So I have, what we're going to do is this step function is going to introduce an e. So we get e to the a is 5, so you get negative 5s, okay, times the Laplace of, okay, f shifted. So I'm going to shift this function. Wherever I see a t, I'm going to write it as what? T plus a. So a is 5, so t plus 5. So this becomes t plus 5 minus 5 over 5. Plus, there's a step function here that will introduce a e to the minus 10s times the Laplace. I'm going to shift that too. This time I'm going to shift it by t plus 10. So wherever you see a t, write it as t plus 10. So you get 1 minus t plus 10 minus 5 over 5. So that's what we end up with. Okay. All right. A lot of this will clean up nicely. So this is 0. This is 0. So we can combine these two and pull out big Y out. So we get big Y s squared plus 4 is equal to, out here the 5's will cancel, so you just get t over 5, okay, which you can pull the 5 out, 1/5 out, so you get Laplace of t. What is Laplace of t? 1 over s. So that's what you'll end up with. Okay, I'm sorry, Laplace of t is what? 1 over s squared. So you get e to the minus 5s times 1 over 5s. The 5 comes from the constant that got pulled out, and Laplace of t is 1 over s squared. I keep saying s, it's 1 over s squared. Plus, we get e to the 10s. Out here what will happen? When you simplify this, you get 1 minus t plus 5 over 5, because when you add the 10 and the negative 5, and if you split up the numerator, we get 1 minus t over 5 minus 1, because 5 over 5 is 1, and you distribute this negative, the 1's will cancel, so you get negative t over 5. So what is Laplace of negative t over 5? I can pull the negative 1/5 out and take the Laplace of t, which will just be s squared again. So we'll get negative, so this positive will become a negative. We get 1 over 5s squared. So we get the same thing. All right. Next we divide by s squared plus 4. So we get e to the minus 5s times, I'll put the 5 out. I get 1 over s squared times s squared plus 4. You notice I didn't combine these two. I can't because of these exponentials. Minus e to the negative 10s over 5 times 1 over s squared times s squared plus 4. Now you might think this is a lot of work, but technically these two are exactly the same. So I need to do partial fraction decomposition just once. Is that okay? So that's all I need to do. Remember, when you do partial fraction decomposition, you always leave the e's outside, okay? Because you can't do partial fraction decomposition with those. So now we do PFD. Again, for the sake of time, I am not going to do that. You guys know how to do PFD. So we get e to the minus 5s over 5. If you recall this, if you were doing partial, it'll break into a over s plus b over s squared plus cs over s squared plus 4 plus d over s squared plus 4, and then you will find those constants, okay? And again, I've done this before, so I don't have to waste time. So I get 1/4 over s squared minus 1/4 over s squared plus 4. That's what you end up with. So that'll be the same over here, since both of these are exactly the same. I get 1/4 over s squared minus 1/4 over s squared plus 4. Okay, we're almost done. Now we did the decomposition. Now the only thing left to do is inverse Laplace. And you can see how ridiculously easy this is compared to having to do this problem 3 different times. I hope you guys appreciate the motivation here, why we need to study the step function and Laplace transforms. Okay, and why is this important? A lot of the times, like if you're as an electrical engineer, you might be doing a problem where you have certain voltage between a certain type, and then you have a different voltage increasing, and then it's stabilizing again, so you have a lot of different situations where stuff like this arises. Or even like if you have a mass spring problem, you have no external force, then you apply some type of an external force to the mass, and then you apply a constant force after a certain time. Okay, so these are a lot of nice real life examples. So Laplace of big Y is little y of t. All right, now comes the fun part of doing these. Okay, anytime you see an E and you're doing inverse Laplace, that introduces a step function, so you get u of 5 over 5, because that's that 5. Okay, then you take Laplace of each of these and you shift them by 5 units. So 1/4 is a constant, so I'll ignore that. What's the Laplace of 1 over s? It's t, so I'm going to shift that. So you get 1/4 t minus 5. Okay, minus, now if I take the 1/4 out, I get s squared over 4. That looks a lot like sine. Okay, but I need a 2 on the top. So if I put a 2, I'm going to need a 2 on the bottom here. So 4 times 2 is 8. So you get 1/8. Okay, then you'll get sine of 2t. But again, you have to shift it. So it's going to be sine of what? This is going to be sine of 2t, 1/8. You're going to shift that t by 5 units. So it's going to be 2 times t minus 5. I hope you guys follow what I'm doing. Okay, and then what are we going to do? Okay, with this. Okay. We shifted that, we got that. We're going to do the exact same thing again. We don't have to do any extra work because we already found those things. Only thing different here and here is the shift. Out here the shift was 5 units. Out here the shift is going to be 10 units. So we get minus u of 10 over 5. This will give us 1/4 t minus 10 minus 1/8 sine of 2 t minus 10. So that is technically your solution, but like I said, we should always write this as a piecewise function. And again, for the sake of time, since I have a few more things to do, I'll just get you started. Out here, how many step functions do we have? 2. So we start at 0, we're going to go to 5 and then to 10. How many regions do we have? How many time slots do we have? 1, 2, 3. So we have 3 pieces to worry about. Okay, in the first piece, since this function comes on at 5, it's going to be 0 in the first piece. I'll use green for that. And after that, this function u of 5 will always be 1. This function comes on at 10, so I'll use a different color, blue. So it's 0 until then, and then it's going to be 1. So if you were to write this as a piecewise function, you would have 3 pieces. From 0 is less than t is less than 5, and then 5 is less than t is less than 10, and t is greater than or equal to 10. In the first piece, both these step functions are 0, so they'll make the whole thing 0. And after that, the green function, this u of 5 is 1, and u of 10 is 0, so this is gone. So you just have this left. So we have 1/5. Don't forget that 1/5. So you get 1/5 times 1/4 t minus 5 minus 1/8 times sine of 2 times t minus 5. And then you can do and then after 10, this is 1, this u of 10 is 1, so this is present, and this is present, so you write this whole thing here. Okay, without the u's though. Okay, and that's the answer to that problem. So I've done 2 examples, and the rest of the problems are exactly the same. We've done this in stages, so you should be able to handle this easily. What I want to do next though is I want to talk about periodic functions. So let's work on that and how to take Laplace of that. So this is periodic functions. Okay. I think I've mentioned once before what periodic function are, but let me go ahead and give that definition again. A function f of t is periodic with period t okay, if this happens, f of t is equal to f of t plus capital T. That means if you were to add capital T to little t, you just get f of t back. It comes back to the same position. Okay, that is the function repeats itself every t units. So that's what a periodic function is. The classic example of a periodic function is sine and cosine are periodic every 2 pi, tangent is periodic every pi. Okay, so we want to be able to find Laplace transforms of periodic functions. Okay, we know how to find Laplace transform of sine and cosine. We know that. Okay, you know Laplace transform of sine is what? It's 1, depending upon what the angle is, 1 over s squared plus 1. If you have sine of t, if you have sine of b, this would be bt, this would be b squared here. Okay, we know the Laplace transform of cosine, but what happens when we have some other type of generic periodic function? How do we find the Laplace transform of that? And that's what we want to work on here. In many mechanical spring problems, there could be where like I've given you an example where you're swinging. If you're swinging, if you at a certain time you pump up so that you can swing higher. So at the apex of the swing you pump up, so you every time you reach that point you pump up, so you're being periodic there. As soon as you go up you pump, as soon as you come back you pump, so every time you reach that point again you pump up. So that's doing a periodic motion there. Okay, in an electrical circuit you could have current that comes on and off and at a set interval. Okay, so that would be another example of a periodic forcing function. So there's lots of forcing functions that are periodic, so we want to be able to take Laplace transforms of those types of forcing functions. So let's take a look at that. How do I find the Laplace transform of a periodic function? And once again, for the sake of time, I'm not going to go through all the details, but if you're interested, please shoot me an email and I will show you how to find the Laplace transform of a periodic function. Okay, right now I'm just going to give you the formula. So the Laplace transform of little f of t, which is a periodic function. So this is periodic period t. Okay, is equal to the integral from 0 to capital T, the period. We have e to the minus st. You have f of t dt divided by 1 minus e to the minus s capital T. So that is the formula for the Laplace transform of a periodic function with period t. Now this on the right hand side looks very similar. If I didn't have this capital T, if I had infinite here, this would be the Laplace transform of f of t. That's exactly what that would be, but we have capital T there. So there's another option for this. We can also use this formula instead. We get Laplace transform big F, I'll put a t there because that's of period t, s divided by 1 minus e to the negative st. So this is a little bit different. This is not Laplace transform of little f, it's Laplace transform of a periodic function. That's why we're using a capital T. That's what this is. Okay, all right. So this is the formula and I'll show you how to use this. Okay, so let's take a look at an example. So let's take one of the classic example of a periodic function is the square wave function. Okay, which is defined as this: g of t, okay, is equal to 1 if 0 is less than t is less than 1, and 0 if 1 is less than t is less than 2. And they've told us that the period of this function is 2. What does that mean? That means g of t is equal to g of t plus 2. So every 2 units it's going to repeat itself. All I need to do is, and that's 2 units, right? 0 to 2, that's 2 units. So once I graph this, I just need to repeat that graph again and again. So let's graph this first. this would be a classic example in a circuit where you're turning the switch on for 1 second, then you're going to turn it off for, turning the current on for 1 second, then you're going to turn it off for 1 second, then you're going to turn it back on, turn it off, turn it back on, or lights blinking or something like that. Okay. All right. So this is 1. So from 0 to 1 to 2 to 3 to 4 and so on. Okay. So what does this look like? Okay. So it from 0 to 1, from 0 it's 1. So we have 1. Then from 1 to 2 it is 0. Then it's going to go back. Now it's going to repeat itself. It's going to be 1. Then it's going to be 0. Then it's going to be 1. And then it's going to be 0 and so on. So you can see this is a periodic function. And it's also called the wave function. In an oscilloscope it looks something like this. Square wave function. Okay, that's what it's called. Okay. All right. Okay, now that we have that, how do I find the Laplace transform of this? I'll show you using both of these formulas, and once you see them, you'll notice this is extremely easy. And that's what you should always use in the future. Okay, but let me show you this example using both formulas. All right, so method 1. I want to take the Laplace transform of g of t that I just gave you. And according to that, the formula is 0 to 2, because the period is 2, e to the minus st g of t times dt divided by 1 minus e to the minus 2s, because t is 2. Now what is g? Well, g is right here. It's defined right here. So I need to split up that integral. I need to go from 0 to 1 and then from 1 to 2. Okay, so I need to split up that definite integral that I have here, and this I can pull out because that's just a constant. So I'll just pull that out, 1 minus e to the minus 2s. Okay, so then I'm going to go from 0 to 1, e to the minus st, g is 1 between 0 and 1, and then after that from 1 to 2, g is 0 dt. So this is just going to be 0, so it's gone. Okay, we just need to integrate this. That's a very trivial integral. We get 1 minus e to the negative 2s. Okay, I get e to the minus st over negative s if you do a u substitution for the exponent. We get this when we plug in the upper limit and the lower limit. We get this. We get plug in the upper limit, we get e to the minus s over negative s. And then when you plug in, upper limit, when you plug in the lower limit, there's a negative here, so that'll become a positive 1 over s. The denominators are the same. Okay, so we can rewrite this as 1. So this, if you notice, can be written as 1 minus e to the negative s over s, because you just rearrange this, move this there, this in the front. The denominators are the same, so we get that. So we get 1 over 1 minus e to the negative 2s times 1 minus e to the negative s over s. Okay, I can do a little better job. If you think about this guy here, it's 1 minus e to the negative 2s. Isn't that the same as 1 minus e to the negative s and then 1 plus e to the negative s? If you were to FOIL this, you would just get this difference of 2 squares. So I can do that. I get 1 minus e to the negative s, 1 plus e to the negative s times 1 minus e to the negative s over s. These will cancel, so we get the nice Laplace transform of the square wave function. It is 1 over s times 1 plus e to the negative s. Okay, so that is the answer to that problem, how to take Laplace of that. Now let me show you method 2. Method 2 tells us to what? Only worry about the Laplace transform up to t, sort of. So the first thing I'm going to do is write this function using a step function. So let's do that. So what is g of t? Well, it comes on between u of 0 minus u of 1 plus between u of 1 minus u of 2, it is off. It comes on between u of 0 and u of 1 and the value is 1, and between u of 1 and u of 2 the value of the function is 0. So that's what we get. So this is just 0 times that is just 0, so we're done with that. So that's what g is. G of t then is just u naught minus u1. So now, if I want to find the Laplace of this, okay, I'm sorry, of the, of this, I get big G of s, or you can write it this way, doesn't matter, is equal to, it's going to be g of t of s, that's why the t, over 1 minus e to the negative 2s. Okay, so you transform this to get this, and then you just have that denominator. Okay, so let's do that. So we have g of s is equal to 1 minus e to the negative 2s. Okay, so what do we get? What is Laplace of u naught? It's 1 over s, minus, what's Laplace of u1? It's e to the minus s over s. So if you clean this up, you get g of s is equal to 1 minus e to the negative s over s, and then I can FOIL this bottom just like I did before. These will cancel, so we get this, and there's your answer. You can see this is a lot more quicker, especially if the functions are complicated. This was an easy function because 1 and 0 were the values. Okay, again, when you use this formula, the Laplace of little g is going to be big G, and on the top we get g of ts, where you're just taking the transform of that step function that you create up to that period. Do you follow? So this should be a 2 technically, up to that period. Okay, so let's take a look at another example and see if we can do the same thing using the second method without having to integrate that. Okay, so let's take a look at another classic example. This is called the sawtooth function. Okay, it looks something like this. We have f of t is equal to t if t is between 0 and 1, and it's equal to 2 minus t if t is between 1 and 2. Okay, between 1 and 2. And the period over here, t is equal to 2. So it's going to repeat itself every 2 units. Okay, so let's first graph it, and then we'll go ahead and take a look at what it is, how to find the Laplace of that. So let's say this is 1, 2, 3, 4, 5, 6, and this is 1. So between 0 and 1 it looks like t. T is just a diagonal line. You guys know that, right? So that's what that looks like. Between 1 and 2, from here to here, it looks like this. So it's negative t plus 2. Okay, so in this case, if t is 2, you get negative 2. Negative 2 plus 2 is 0, so you'll get this point. And if t is 1, you'll get negative 1 plus 2 is 1, so you'll get this point. So if you connect those two, we'll get this piece. Once you draw that first period, because the period is 2, so once you draw the graph from 0 to 2, for that period, the rest is just going to repeat itself. And you can see why it's called the sawtooth function. Okay. All right, let's take the Laplace of that. So we're going to use this handy dandy formula. So the Laplace of little f of t, since it's a periodic function, it is going to be big F of t of s divided by 1 minus e to the negative st. That's a formula we're going to use. So the first thing we need to do to use this formula is write little f as a step function and then take the Laplace that goes here. So this is the Laplace of the step function. Okay, I might want to write that down here. Maybe that'll help you guys. So over here, this guy is the Laplace of the unit step function. Okay, all right. Once you write f in terms of that, little f. So the first thing I'm going to do is write f in terms of that. So if you notice, the first piece comes on at 0 and stays on till 1. So you go from 0 to 1, the value is going to be t. So we get, I'm just doing some scratch work on the side. So we get t, you get u of 0 minus u of 1. And after that, it's going to be 2 minus t. So we get plus 2 minus t. It's going to be u of 1 minus u of 2. That's only up to that period. And then we rearrange this. So we get t of u naught plus t of u1 plus 2 minus t of u1 minus 2 minus t of u2. So we're just distributing and collecting stuff. I'm not collecting stuff, just distributing. Let's collect now. T of u naught plus u1. This is u1. This is u1. So if you add them, the t's will cancel. So you'll just get negative t. Okay. So that's what you'll end up with. Is that right? Let's see. Make sure I can do that correctly. We get oh no, this, when you distribute it, this will be negative, so I did that wrong. So you'd actually get 2 minus 2t of u1, and then you'll end up with the last one is going to be minus, I'll put a plus here, you get t minus 2 of u2. Okay, that's what you'll end up with. So that's the step function. Okay, so now to be able to do this, what do I need to do? Okay, to take the Laplace of this, I get Laplace of little f of t is equal to 1 over 1 minus e to the negative 2s, capital T is 2, times the Laplace of this guy, f of t. Okay, now keep in mind, I know I'm using f of t very loosely here. Okay, this f of t is different than this f of t because this is only for one period. This is for the whole f of t. So if you want, you might want to put a little t here. That'll make more sense then. Okay, so if I take the Laplace of that, I get big F of t. So let's take that. What's the Laplace of this? T times t naught. What's the Laplace of t? 1 over s squared plus, anytime you take a Laplace of u other than 0, you get e to the minus s because a is 1 here. And then you take the Laplace of each of these and shift them. So we get 2 minus 2 times t minus 1 because you would shift them. Okay, so please keep that in mind. Okay. All right. Then what are we going to do next then? Oops, this time I do need a plus. Then we get plus u of 2. That'll give me e to the negative 2s times the Laplace of this guy shifted. So wherever you see a t, you get t plus 2 minus 2. So this will cancel. When you distribute out here, this will simplify to just negative t because you get negative 2, which will cancel with this positive 2 in the front, and you get negative 2t. So if you do that, we get 1 over 1 minus e to the negative 2s. We get 1 over s squared plus we get e to the negative s. What's the Laplace of just this? Laplace of t is 1 over s squared. The negative 2 will just come out, so this will become 2 over s squared. Okay. Oops, that 2 should be on the top. My bad. Because that's on the top. Okay. Plus Laplace of t, which is e to the negative 2s over s squared. So that is the Laplace of little f of t. Now technically you can simplify this if you really wanted to make it look pretty, but that would be a perfectly good answer. The common denominator is the same. We get 1 minus 2 e to the negative s plus e to the negative 2s. The top should look familiar because if you were to expand this, if you were to square this, you'll get exactly this. So I can write it as 1 minus e to the negative 2s times 1 minus e to the negative s squared over s squared. Okay, what does that do? well, let me rewrite this differently. I showed you how to rewrite this. 1 minus e to the negative s, 1 plus e to the negative s. So one of these will cancel. And then you get a nice answer for the Laplace of what we wanted to do. We get 1 minus e to the negative s over s squared times 1 plus e to the negative s. So that's a much nicer answer than what we had before. Okay, so that's how we take Laplace of periodic functions. Okay, I am a little over. Let me just give you an example of this. I won't get to the gamma function like I wanted to, but let me go ahead and give you an example of why this is all useful. Okay, why the Laplace of periodic functions are useful. So let's say you have an RL circuit. Okay, where L is 1, the resistor is 1 ohms, and the electromotive force is given by the wave function. So it looks something like this. It's 1, then it's 0, then it's 1, then it's 0, then it's 1, oops, then it's 0, sorry, and so on. So this is a square wave function that we did before. And we know the Laplace of that. We just did that. That was the very first example I did for that reason. Okay. So if you remember from chapter 3, I can rewrite the RL circuit differential equation as L times di over dt, the current, okay, plus R times I is equal to E of t. And they've given us some initial condition. The current at time 0 is 0. Again, I do know this, okay, this is a square wave function that I did right here. Right here. It's the same function, okay? So that's what that is. So let's go ahead and plug in our values. R is 1, L is 1, so we get I prime. I'll just write it as derivatives. I prime plus I is equal to e to the t. Okay. Now I take Laplace on both sides. Laplace of the first derivative is just s times big I, okay, minus I prime of 0 plus the Laplace of little I is big I is equal to Laplace of e. I did that for you earlier. It was 1 over s times 1 plus e to the minus s. You can go back in your notes and look at it. That's what we did earlier, just 5 minutes ago. All right, so let's solve this. So I can, this is 0, the initial, this is not prime, this is just I. This is 0, so you can pull a capital I out. We get s plus 1 is equal to this. And we get I is equal to 1 over s times s plus 1 times 1 plus e to the negative s. Now please remember, what did I tell you earlier today? We can only do partial fraction decomposition if you have a polynomial on the top and polynomial on the bottom. Is this a polynomial? No, it's not. So I need to be a little bit creative on how I'm going to go forward. So I can write I as 1 over s times s plus 1 times 1 over 1 plus e to the minus s. I will do the decomposition for this, and I will handle this a different way using something we studied long ago in Calculus 2. Okay, so let's do the decomposition. So I'll do PFD for this. I'm not going to do this. This was a very trivial PFD. You guys can do that. Okay, what I want to concentrate on is this guy. So let me call this star, and let's see how to deal with that. So from Calculus 2, okay, if you remember, we studied power series. You think you forgot all about that? We have to do a lot more power series in this class. So if you remember, we did this power series. We 1 over 1 minus x. Okay, if you recall, it was 1 plus x squared plus x cubed plus dot dot dot. In a compact form, we wrote it this way: 1 to infinite, x to the n. I hope some of you remember that. If not, it's a good reminder here. That's a power series for 1 over 1 minus x, this function. Remember, a power series is just a polynomial, which is what I have. If you look at the star and look at this, they're pretty much the same. The only thing different is out here we have e to the minus s, out here we have negative x. Okay, so I can rewrite this as 1 over 1, okay, minus e to the negative s. If you remember in Calc 2, if I wanted to find a power series for 1 over 1 minus x squared, we put an x squared here, and everywhere we see an x, we squared it. Do you guys remember that? So that's all we're going to do here also. Okay, we are changing x2 minus e to the negative s. So wherever we see an x, we're going to change it to negative e to the negative s. So let's do that. So we get 1 minus this x will become this e to the negative s, plus, because you take negative e to the negative s and you square that, this negative will become positive. You get e to the negative 2s. If you cube it, this negative will become a negative. You get e to the negative 3s plus e to the negative 4s minus e to the negative 5s, and so on. You can write it in a summation form more compact. I really don't want to do that. All right, so let me call this 1. So let's go back to 1 now. Okay, so what does 1 become? Okay, I have I on the left is equal to, I need to do the decomposition for this, which is really trivial. It's 1 over s minus 1 over s plus 1. That's a decomposition for this guy. And then this stays the same, 1 over 1 minus e to the negative s. Actually, I'll write it this way. Minus of 1, minus e to the negative s. That'll give you a positive in the middle that we want. Okay. Now this looks familiar. Isn't that what we just did here? So I can replace this guy here with this, which in turn is this. So let's do that. So we get I is 1 minus s minus 1 over s plus 1 times 1 minus e to the negative s plus e to the negative 2s minus e to the negative 3s plus e to the negative 4s, and so on. Okay. All right, this is really getting interesting because we're going to infinite here, aren't we? Okay, so we're going to go ahead and distribute. We're going to distribute this 1 over s and then this. So we get I is 1 over s minus e to the negative s over s plus e to the negative 2s over s, and so on. That gives us the first part. I'll put brackets. Plus, I'm going to go ahead and distribute this negative. So we get negative 1 over s plus 1 plus e to the negative s over s plus 1 minus e to the negative 2s over s plus 1, and so on. Okay, now we can do the inverse Laplace because these we can handle. So we get little I of t, since it's a function, current is a function of time. What is inverse Laplace of 1 over s? It's 1 minus, what's the inverse Laplace of this guy? Well, remember, whenever you do an inverse Laplace with an e, you introduce a step function. A is 1, so you get u1, and the Laplace of s is just 1. Okay, plus, what's the inverse Laplace of this? You get 1 times u2, because now you'll get u2. Then you'll get minus 1 times u3, and so on. I hope you get the idea. Okay, plus this one, if you take the inverse Laplace, you get negative e to the negative t. Now we get something interesting to pop out here. Anytime you have e, you get a step function. So you get u. But the inverse Laplace of 1 over s plus 1 is e to the negative t. But because you have this e, you're going to shift this also by negative 1 because a is 1. So you get e to the negative t minus 1 u1. Okay, minus e to the negative t times t minus 2 u2, e to the negative t minus 2 u2, because this will cause the u to show up, and then we take the inverse of 1 over s plus 1 and you shift that. So we get that, dot, 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 that continues. So that's what we end up with. Okay. And this is a perfectly good answer to this problem. If you wanted to, you could be really creative and write it using a summation notation, because this is easy to write as a summation. So is this easy to write as a summation? But for now, I'll just leave it like this. Okay, so you can see how we use the periodic nature of the current coming on and off, or the circuit being turned on and off, to solve a RL circuit problem using Laplace transform. Okay, so I am done with this section, but I would really like to do the gamma function because I think it's an extremely interesting function, and that will take me a little bit to do. So let me go ahead and quickly do a little bit of it, okay? Just so I feel comfortable that I've done everything I need to do. EF. Okay. So this is the gamma function. Okay. So the gamma function is defined by this. It's a Greek letter gamma of some k is equal to, it's an improper integral from 0 to infinite. We have x to the k minus 1 times e to the minus x dx. So it's a pretty funky looking function. The gamma function is called, the gamma function is a generalized factorial function. That means it acts a lot like a factorial, but if you recall factorial, just a quick reminder what a factorial is. If you have 5 factorial, we get what? 5 times 4 times 3 times 2 times 1. Okay, but you can only take factorials of positive integers. This has to be a positive integer. The gamma function acts like a factorial where this can be anything. Do you guys follow? It can be a decimal, it can be a fraction, it can be negative, it can be anything. If it is an integer, then the gamma function will do exactly this. If it's not an integer, it'll still give you some type of a factorial, because you can't take factorials of decimals or negative numbers or fractions, but it'll act like that. Okay, that's why it's called a generalized factorial function. When it is an integer, it'll act exactly like a factorial. Okay, so here are some properties of gamma function. And just because of time, I'm not going to prove anything. If you are interested, always shoot me an email and I will prove I'll show you how to do all of these properties. So the first property of the gamma function is gamma of 1 is equal to 1. You can use this formula here, replace k with 1 here, and you can figure it out. Okay. The second property is gamma of k plus 1. Okay. Is going to be, what do we do? In this here, replace k with k plus 1. So when you replace this with k plus 1, the negative ones and positive ones will cancel. And then you do integration by parts, and you'll end up with this handy dandy formula, k times gamma of k. Okay, so that's what you end up with. You basically get the gamma function back, except multiplied by k. Now comes the interesting part. Remember, I said gamma function is like a generalized factorial function, right? So why is that? Let's take a look at that. If k is 1, k is an integer, positive integer. If it's a positive integer, it should act like a factorial. So let's see. We get what? Gamma of 2 here, which is 1 times gamma of 1. We know gamma of 1 is 1, so we just get 1. What happens if k is 2? Oops, 2. We get gamma of 3 here because we get k plus 1. I'm using property 2 here. We get k, which is 2 times gamma of 2. Gamma of 2 was what from here? 1. So we get 2 times 1. So looks like a factorial. Let's do one more. 3. What is gamma of 4 then? That'll give you gamma of 4. So it'll be k, which is 3 times gamma of k, which is 3. K is 3 here. What is gamma of 3? We just did that a minute ago. It's 2 times 1. So you get 3 times 2 times 1. I hope you guys can see what's happening here. So in general, So if k is a positive integer, okay, that is k is equal to some n, just a positive integer, then what do we get from up here, from if you use that logic? What is gamma of n plus 1? What happens here? If gamma of 2, we got 1. Gamma of 3 gave us 2 times 1. So this is like 2 factorial. If gamma of 4, we got what? 3 times 2 times 1. That's 3 factorial. So whatever this number is, we get 1 less factorial. So in this case, if you start with n plus 1, you'll end up with what? N factorial. So here's a nice property of the gamma function. Acts like a factorial. Okay, that's why it's called generalized factorial function. The next property is, if you think about it, property 2 told us what? Gamma of this is that. So if you divide both sides by, actually I'm not going to do that property, that's in ODEs, but let me go to the next one. Gamma of 1/2, which is another very important gamma value you should always know, is equal to square root of pi. Many times I give this as an assignment for students to do, because this involves Calc 3 double integrals. Since we have a lot of students who haven't taken Calc 3 yet, this will be hard to assign you. But if you all had taken Calc 3, you could easily do this, show this using double integrals, okay, from Calc 3, and changing the order of integration, if you recall in Calc 3 that we do. So this is really a cool property, because now we can see we can take gamma of fractions here. So what about gamma of minus 1/2? Okay, well, if you use this property, let me go back here. This property, a variation of this property is what? Gamma of k is equal to 1 over k times gamma of k plus 1. I'm just dividing both sides by k. Okay, so that gives you that interesting property. So let's use that instead. So this is going to be my k. So it's according to that property, it's 1 over k, so 1 over minus 1/2 times gamma of k plus 1. That's what we'll get. So if you simplify this, what do we get? We get negative 2 gamma of 1/2. But I do know that gamma of 1/2, which is what? Square root of pi. So that's what you get. So you can do all kinds of gamma functions now. Okay, all I did is use this property here, just a variation of this property. I gave you this, and then you can use a variation by solving for gamma of k. All right, so that gives you that. All right, so those are some good properties of gamma. You can figure them out. You can also do gamma of negative 3/2 and so on, and you get some interesting looking graphs and things like that. But the reason for doing all of this has to do with Laplace transforms, obviously. So let's take a look at 5. Let's say that if I give you this function, f of t is equal to t to the a. Now a can be anything over here, where a is a real number. Now keep in mind, if f of t was t to the n, where n is an integer, then I know the Laplace transform of that. If you recall, what is it? It's n factorial about s over n plus 1. But now we are saying we don't have an integer there. We have just some number. A can be anything. So what is that? According to the properties of gamma, the Laplace transform of t to the a, where a is anything, is going to be 1 gamma of a plus 1 divided by s a plus 1, provided s is greater than 0. So this is the Laplace transform of t to the a, where a is any real number. So let's take a look at an example. So what is the Laplace transform of t to the 1/2? I can't use this, because do I know 1/2 factorial? I do not know that. So I get gamma of a is 1/2, so I get 1/2 plus 1 over s raised to 1/2 plus 1. Okay, which we can simplify a little bit, which gives us what? Gamma of 3/2 and s raised to 3/2. Okay, what is gamma of 3/2? Well, how do we do that? I'll do it on the side here. we use this property, gamma of k is equal to 1 over k times gamma of k plus 1. Okay, so how would we do that? What is gamma of 3/2? So help me out. How do we do that? Okay, so we get, actually I'll flip this around so we can do this a little bit better. Okay, yeah, let's do that. So what do we get? We want gamma of, I'll just write this way. Gamma of k plus 1 is equal to k times gamma of k. Okay, if you look at it, k is what? Half. So we get gamma of 1/2 plus 1 is equal to 1/2 times gamma of 1/2. This is just gamma of 3/2, which will give you 1/2 times square root of pi, because gamma of 1/2 is square root of pi. So this gives us 1/2 times square root of pi times s raised to 3/2. And that is your answer for gamma of t to the 1/2, which is really cool that you can do these really goofy Laplace transforms of goofy exponents using gamma function. Okay, before I end, let me just wrap this up by showing you what will happen to property 5 if, so in property 5, if a is equal to a positive integer, okay, that is a is equal to some n, then what happens to that property? So Laplace of t to the n is equal to, in property 5 here, right there. Remember, now a is n, this will be n, this will be n. So we get gamma of n plus 1 over s to the n plus 1. Okay, but what is gamma of n plus 1? It's right here. Gamma of n plus 1 is n factorial. Well, so this gives you the formula that we already knew, which gives us n factorial over s to the n plus 1. This is the formula we derived in class for the Laplace of a power function where n is a positive integer. Okay, so we can verify that this formula is a more general formula. So you can see how the gamma function is a factorial function because you generate the factorial there. Okay, that's pretty much it for the gamma function.